Continuing our discussion of real zeros, we have looked at this idea that if r is a real zero, then x minus r is a factor of your polynomial. So you have this relationship then between your real zeros and your factors. Well, here I have an example of a polynomial that does not have a factor, or has a factor that is not in the x minus r format. Okay, it's actually 2x minus 7, which is a little bit different. So the x minus r requires there to be a 1 as the leading coefficient there. Okay, so I'd have that with the 5, but not in the 2x minus 7 portion of that polynomial. And so what I want you to see, though, is that you can still get zeros, real zeros, out of a factor that looks like this. It's kind of like an mx plus b sort of format, like a slope-intercept form, right? So to find the zero, you take that factor, set it equal to 0, because of course if that factor is 0, then the whole function is 0, and you solve for x. So you get 2x equals 7, divide out the 2, and we get x equals 7/2. Now according to what I have written here, if r is a real zero, then x minus r is a factor. Well, I don't have x minus 7/2 as a factor. I have 2x minus 7 as a factor. But interestingly enough, one can be written as the other if you were to consider factoring out a 2 from the original factor. Okay, so consider this. If you were to take the factor 2x minus 7 and you were to consider that there's a common factor of 2. Now it doesn't appear that there's a common factor of 2 because the 7 is not divisible by 2. But if you factor out, it's basically the distributive property in reverse. If you factor out a 2, then you're essentially dividing each term by 2. And so the first term would become x, the second term would become 7/2. Okay? And you can always check that by redistributing, right? 2 times x is 2x, 2 times 7/2 is 7. Okay, so just redistributing gets us back to the beginning. And now I could rewrite this 2x minus 7 factor in such a way that I do have the x minus r, or x minus the real zero, okay, as the factor. And so my equivalent form of that polynomial, I could write it as f of x equals 1/3. Now instead of 2x minus 7, I'm going to write it as 2 times x minus 7/2, and then I have the x minus 5. Okay. All right, so my real zeros in this case are the 7/2 and the 5. Okay, so the real zeros are 7/2 and 5. And my leading coefficient now is the combination of these two coefficients. It's actually 2/3, right? 1/3 times 2 is 2/3. So the final form, I could really combine these into the leading coefficient of 2/3. Okay. All right, so I think that's important because usually when we write these out, we leave the zeros as like whole numbers or integers, but they're not always that way. Sometimes they're rational numbers. They could even be irrational numbers. Some other interesting combinations that you might see are going to be factors that maybe are quadratic in nature, but they don't factor using the integers. All right, so something like maybe my polynomial has x squared minus 2 and x plus 3 as its factors, and you want to know what the real zeros are. Well, obviously -3 is one of them, right? So if I list out the real zeros, one of them is -3. but I can also get some real zeros off of this x squared minus 2, right? So if you think about how to find those, you would take x squared minus 2, set it equal to 0, and solve for x. Well, it's not easy to solve for x because I can't just factor this apart. I would have to add the 2 to both sides and then apply the square root property, which says that x is equal to plus or minus the square root of 2. Well, if plus and minus the square root of 2 are both real zeros, okay, now I've got 3 real zeros in there, then that must mean that x squared minus 2 is actually factored into x minus root 2 and x plus root 2. So that the original polynomial really factors into, it factors further, okay? So even though x squared minus 2 is not factorable over the integers, it is factorable over the real numbers by using square root of 2, okay? And hopefully you'll recall that anytime you have a difference of squares, it factors into 2 conjugates. Okay, this is a property of algebra that I think is very important. Anytime you have something that's in the form a squared minus b squared, it will factor into the conjugates a plus b and a minus b. Remember, conjugates are the same 2 terms, but they differ by the operation in the middle. Okay, one's a plus, one's a minus. All right, so when you have 2 conjugates, if you multiply these 2 conjugates together using distributive property, they simplify down to a difference of squares. Usually you'll see this in your beginning algebra classes, your intermediate algebra classes, with examples like x squared minus 9, where both terms are perfect squares, and you can factor them into x plus 3x minus 3. But here, in x squared minus 2, it doesn't appear that these are perfect squares. But every number is the square of something. You just have to find out what it is the square of. And in this case, it's the square root of 2. Okay, okay, so those are a couple of interesting differences where it doesn't seem like they fit the the idea of a real zero having a factor of x minus r, but they do in the end. We just have to be clever in how we construct those zeros. Okay. All right, so now the next idea sort of encompasses all that stuff, because we're going to focus in on the rational zeros. That last example with the square root of 2 in it, those are irrational numbers. Rational numbers can be written as fractions, like the 7/2 in the first example. Okay, so we're going to look at something called the rational zeros theorem. Rational zeros theorem. It really helps us to identify, just off the coefficients of the polynomial, what the rational zeros could be. Okay, let me give you a quick example to motivate this theorem. If I had a polynomial that was factored into 2x plus 3 and 4x plus 5, if I were to distribute this out to get my terms of the polynomial, the standard form, this would be what? 8x squared plus 10x plus 12x plus 15, which simplifies to 8x squared plus 22x plus 15. Okay, so that's the expanded form. But if I want to find the real zeros of this thing, I go back to the factored form, right? So the real zeros are found by setting each factor equal to 0 and solving for x. Here I would subtract the 3, I get 2x equals negative 3, and then I divide out the 2, I get x equals negative 3 halves. Okay. On this one, I would subtract the 5, I get 4x equals negative 5, and then divide out the 4, I get x equals negative 5/4. Okay. And so what you'll see, whenever you have rational zeros, these are rational because they're fractions, the numerators, notice the negative 3 and the negative 5, the numerators will always be factors of the constant term in the standard form. The denominators, notice the 2 and the 4 there, the denominators will always be factors of the leading coefficient. So if you were to look at the standard form of a polynomial, and you take all the factors of the constant and divide them by factors of the leading coefficient, you'll get a list of numbers that will include every rational zero. Okay? And in this case, in this particular case, if I was given the standard form and I didn't know the factored form, then I could find a list of zeros, a list of rational numbers that includes these zeros. Okay? And I could do that simply by taking, let's pretend I don't know the factored form. So I'm going to do that by taking the factors of 15. I'm going to call the rational zeros, I'm going to call them P over Q, so I can kind of have a variable to designate the top and the bottom. The P's, remember, P is a factor of the constant, we'll call it A sub 0 in the standard form, and Q is a factor of the leading coefficient. We'll call that A sub n in the standard form. Okay, so P over Q. Now in this particular example, I'll erase a little bit of this, but I'll keep the zeros set aside here just so I can reference back and make sure I got this right. Well, you can verify that I got it right. What we're going to do is we're going to list out all of the factors of the constant. Those are the possible numbers that could be used for the numerator. The factors would be plus minus 1. This is any integer that divides 15. Plus and minus 1, plus and minus 3, plus and minus 5, plus and minus 15. So there are technically 8 numbers here that are all factors of 15. Right? The positive and negative version of each of those, 1, 3, 5, and 15. If I look at factors of 8, those would be my denominators. Then factors of 8 are going to be plus and minus 1, plus minus 2, plus minus 4, and plus minus 8. So again, I have 8 more combinations. All right. And so if I were to look for the list of all the possible rational zeros, not the actual ones, there's only 2 actual ones, but the list where they come from would be all the combinations of P values divided by Q values. It looks like it's going to be a lot, it is, but it is less, significantly less than, it narrows it down. If we didn't have this theorem, it narrows down our search. It's less than what we would get if we just looked at the polynomial and we're just kind of guessing at real zeros or rational zeros. So the possible, now again, I'll just set these over to the side, negative 3 halves, negative 5/4. Okay? Oops. Okay, so if I look at all the possible rational zeros, I call them P over Q. I'm just going to list out all the combinations. Now this takes a little while, but if you do positive 1 over positive 1, positive 1 over negative 1, negative 1 over positive 1, negative 1 over negative 1, out of all those options, there's really plus or minus 1, right? That's all that's really there when you simplify it. So I'd say plus or minus 1, and really the positive negative is just going to follow through, so don't worry about accounting for negatives here. You just do 1 over 1 is 1, 1 over 2, 1 over 4, and 1 over 8. Those are the possibilities. So 1 over 2, oops. Let's do that. plus or minus 1 over 4, plus or minus 1 over 8. Okay? And then, of course, if you get anything that repeats or simplifies to something you already have, you can ignore that. So now let's go with a 3. So you get 3 over 1, 3 over 2, 3 over 4, 3 over 8. So that would be plus or minus 3, plus or minus 3 halves, plus or minus 3 fourths, plus or minus 3 eighths. And we're getting a pretty long list, admittedly. Then if I want to keep going, I go to the 5. So plus minus 5 over 1, which is just 5, I don't need the 1 on the bottom. Plus or minus 5 over 2, plus or minus 5 over 4, and plus or minus 5 over 8. Okay, getting a little crammed on the bottom, but hopefully you can see all that. And then finally the 15. You jump to the 15, you get plus minus 15 over 1, plus or minus 15 over 2, plus minus 15 over 4, and plus or minus 15 over 8. Okay, so that gives us quite a long list of possible rational zeros. Now if I created this list, how would I figure out which ones are actually rational zeros? Again, assuming I don't know the factored form of this. Well, one thing I could do is just start plugging them in right from the beginning. It's a lot of things, but remember, if you plug in a number to the original function, let's call this f of x, I lost my symbol there. If I plug in one of these potential zeros into my function and the output is 0, remember the output is the remainder that you get when you divide by x minus, whatever the number is. So if you get out a 0, then you know you actually have a 0. You have something that will factor. In this case, the ones that will work are going to be negative 3 halves, which is on my list right here. That's one of the numbers. And negative 5 fourths, which is on my list right there. Okay, so out of all those possibilities, those are the only 2 that will work. Okay, they will get 0 as an output when I plug them in. In other words, when I plug in all the other numbers here, I'll get something other than 0 as my output. And as soon as I get something other than 0, I just ignore them and move on to the next problem, or the next number, okay? Now obviously this is a lot to check. The ones that you'll see and the ones that I'll do in the next couple examples will have way fewer factors, so they can be much more manageable.